All right, line I1, we're in learning task 1, where we're going to start taking a look at circuit protective types of devices. And the first part that we're going to go into is identification based upon the ratings that we are going to have inside of here. They give us a couple of ratings that we need to know off of these right off the bat. First thing we are going to need to know will be our voltage rating. Then we're going to have a current rating. Then we're going to have an interrupting rating, which is also given in amps, but it will be different than our current rating. And then we are going to go and have a time current characteristic, or basically a response that we are going to go and have. Let's talk about these one by one. The first one that we're going to have is going to be the voltage rating. Obviously, it needs to be rated to be able to handle the system that it is going to be put across there. We are going to be able to go and place sometimes higher voltage components onto lower voltage systems, but never the opposite way around. Because what our voltage rating does is whenever we have got a fuse or a circuit breaker, there's going to be an opening across that fuse or circuit breaker. So if I've got a 600 volts installation over here, when that circuit breaker opens up, or that fuse opens up, what I need to be able to do is interrupt the 600 volts and prevent it from being able to restrike. It has to be a large enough gap. There's different sizes of fuses that are going to have different end-to-end lengths, and therefore they're going to have different abilities to restrike. So we have to be careful how we use them. Could I use a 600 volt fuse on a 300 volt system? Absolutely, because it responds to the current. But could I use a 300 volt fuse on a 600 volt system? Absolutely not, because it would be able to strike across. If this thing was 300 volts rated, here, I'm going to write it actually on the fuse. If this was a 300 volt rated fuse on a 600 volt system, what I would get is that my arc would go and travel all the way across or through inside of there, and it would not be able to safely interrupt. But if this was done the opposite way, where this were to be a 300 volt system and I was using a 600 volt, then absolutely, I would be able to go and interrupt. We would not be able to get any current over top. It would just be impossible for it to bridge the gap that would be created inside of it. There are standard ratings. Now, we do have to be careful with protection ratings on fuses. Protection ratings are fairly straightforward. But when I'm looking at a breaker, those ratings are a little bit more tricky. Let's go into our Canadian Electrical Code. We're going to start inside of Section 2. Section 2 is a lot of general rules, including this whole concept of marking of equipment. And whenever we have equipment that's going to be used in the field, we have to be able to verify a couple of things, the suitability and the approval, and we should be able to find out more information on it. So we get a bunch of things inside of there that are going to be like the maker's name, trademark, or other recognized symbol of identification. That allows us or the inspector to look it up and figure out what it is. Voltage that we are going to go and have. Rated load amperes. We will see both of these inside of what we're looking at inside of fuses and circuit breakers. Then they got a bunch of other things that's not going to be on everyone. Because we only need to have the markings that are necessary to identify the equipment. So for fuses and circuit breakers, volts and amps are going to be necessary. They're also going to go and have a short circuit current rating or a withstand rating. That's going to be the interrupting rating for us, and any other components. When we go down through here, and we'll just skip ahead to this point over here, we are going to find some other specialized ratings over here. So it says, where electrical equipment is marked for short circuit current ratings or withstand ratings, the equipment selected for the installation shall have ratings sufficient for the voltage employed and for the fault current that is available at the equipment terminals. In other words, if I have got a interrupting rating, it has to be suitable. I'm not allowed to use something that's going to have too small of an interrupting rating. We'll talk about that in a minute. And while we're dealing with the voltage, what I wanted to get us through to was this section over here, what we refer to as slash ratings. It says electrical equipment marked with both line-to-line and line-to-ground voltage ratings, such as 125, 250, 122, 40. Those are both describing single ones. 208Y, 120, 480Y, 277, or 600Y, 347 shall be permitted to be connected only in a circuit that is solidly grounded and where the nominal voltage of the conductor to ground does not exceed the lower of the two values, and the nominal voltage between conductors does not exceed the higher value of the electrical equipment's voltage rating. This is going to go and talk about the usage of circuit breakers. We have got single phase voltages, that's what we're working with still inside of second year, that are going to be 122/40. And from a line to a neutral is always going to be 120 volts off those single phase voltages. We do have three phase ones that are going to be 120 208 that are going to have these ratings as well. Where we're once again going to have from a single line to the neutral is 120 volts. But what I'm not allowed to do is, even if it was a single pole breaker, I cannot use something that is good for 122.08 on a 122.40 volt system. So be very careful. If you've got a breaker that has got a slash rating on it, and it says it's 122.40, you cannot use that thing inside of a 122.08 type of panel. Although it looks like it should be able to go and, be utilizable, etc., or 122.08 in the opposite way, you need to be very careful with these ratings. So read the voltage ratings off of them. This is a big deal inside of our Canadian Electrical Code and for our inspectors. They look for this on job sites. All right, going back to this. Next thing that we are going to have is going to be my Ampere rating of a fuse or circuit breaker. That's going to be the maximum amount of current that we could continuously stick through it before that thing is going to go and open. So we could say that this is a 20 amp fuse over here. That means that I can flow 19.9999 amps through it continuously. I can run 20.0000 amps through it continuously, 365 days a year, all day, every day, and it's not going to go and do anything. But as soon as I crack that line, it should respond. Now, it will be imperfect. Some of them might respond a little bit early, some might respond a little bit late, but overall, they should be able to carry the full rated current. But once we go over it, it is going to respond. The amount we go over it is going to determine how quickly we respond. There's going to be, tiny, tiny little bits. This one, we would probably allow that to happen for a long time before we say, okay, enough of that, it's time to shut her down. Compared with, if I have a 20 amp that is going to have 40 amps going through it, we would say that's way too much. We would want to shut that thing down. We'll talk about with that with our inverse time current characteristics in a minute. There are going to be applications where the Ampere rating is going to be higher than the wire size. Usually the Ampere rating is going to be tied to our wire size. We don't want to go and overload our wire. You can go into your table 13 of the code and it gives us a bunch of ratings out of there. There are going to be specialized times inside of Canadian Electrical Code applications that we are allowed to use a larger breaker or fuse than what we have for the actual line conductor. You haven't covered motors yet, but when you cover motors, you're going to find it there. You have covered heaters already. And inside of heaters, you should have seen that going through those calculations, how we end up with a larger breaker than the actual wire sizes that are downstream. But that's because it is permitted. It's a special case that we are allowed. All right, interrupting rating. On this fuse, we are also going to go and have another rating that is going to go and say 10 kA, or it might say 10,000 amps interrupting rating. This is going to be the maximum amount of short circuit current that it would be able to go and interrupt. In other words, the maximum amount of fault that could go and flow through it. When we were going through transformers, we started to take a look at our fault current characteristic. You remember that percent impedance we looked at? This is where that percent impedance and that fault current developed by a transformer has to get matched to my circuit protective device. If I've got a transformer that can put out 20 kA of fault current, I could not use that with a 10 kA rated type of circuit breaker because that circuit breaker would not be guaranteed to be able to interrupt that. We do have two main classes. We have got what we refer to as HRC, our high rupturing capacity is what it stands for. They're going to be rated to 200 kiloamps, 200,000 amps, which is going to be more than large enough for almost every installation that you will deal with. Lots of our other smaller and older components in our circuit breakers are going to have much lower ratings, 10,000 amps, which means that as we get higher upstream, from those devices, getting closer towards the transformer, we're going to have to do some coordination. We're going to have something else upstream that's going to be able to interrupt that. Time current characteristics that we will have. Time current characteristics are going to be how a breaker or a fuse is going to go and respond based upon the amount of fault that we are going to go and have. And they're showing us two main types of, well, not main types, but two specific types of fuses over here. We have got this one, which is going to go and be a time delay fuse. In other words, it is a slower type of fuse because it's allowing us to, say, well, let's just wait and see if this clears itself up. Because in some cases we have small things that happen for a short bit, but then they clear up. So this is going to be a slower one. It's going to be time delay. We're going to go and have this other one, the KTN, which is going to be a fast type. that we are going to go and have. So it's without time delay. If we compare a fault off of that, we will see that we're going to have two separate things that are going to go and happen. Now over here is my current in amperes. These fuses, by the way, are rated for 100 amps, which is going to be their maximum current carrying capacity that they're going to have. So you'll see that these lines stop down here where we've got this line, which is going to go and be my 100. They don't cross over top of that because they should never operate when we have a 100 amp fault inside of them. But anytime that we go past that 100 amp, moving up here, this is called the logarithmic scale, by the way. It's a scale that kind of like compresses and gets larger, compresses and gets larger. As we move past that, we start to see that we start to get operation off of these. Let's go and take a look at operation at 500 amps. Okay, 500 amps is a lot of amps, but if it's a 100 amp system, that's definitely within the possibility of any sort of a short circuit. So at 500 amps, I see that my KTN is going to be operating at 0.2 seconds. But I see that at the same 500 amps, following that one up over here, that my time delay is going to go and wait 10 seconds before it is going to go and blow. This is going to be a time current characteristic that would be useful for something like a motor, where I'm going to go and have a lot of inrush coming into that. Whereas my fast acting, I'm going to want to do that for something that's not going to be motor driven, where I don't have overloads, because I know that the second that I crack over that limit, it's probably got to fall. So you'll select your fuses based upon, should there be any overload. If there's going to be overloads apparent on the system, we will usually start out with a time delay off those. We refer to what we have as fuse coordination or protection coordination, or sometimes selective coordination. Because what we want to have happen is we want stuff that is going to be close to our fault to go and operate first. Let's just draw out a quick example over here. We'll draw it as a one line where I'm going to be coming into my installation, and then in my main part of my installation, we're going to go and have a fusible disconnect. We'll have a fuse inside of there. From that fusible disconnect, we will go out to a splitter, and then off of that splitter, we will go and have another fusible disconnect. And then from that, we will feed that thing into a panel. Oh, why did I feed that into a panel properly? And then that panel is going to go and have its circuit breakers that are going to be inside of it. So I'm going to have differing sizes. This might be a 600 amp for my main. 600 amp over here. Then I might be coming from that 600 amp. I might be dropping down to a 200 amp over here for that fuse. That's going to be feeding this panel that we have over here. Is a load sensor. There's no main breaker on it. And then inside of that, I'm going to go and have some other breakers. We're going to make this one here a 50 amp breaker. So if I've got this 600 amp, 200 amp, and 50 amp, they're all going to be incrementally more expensive. 600s are going to be much more expensive than a 50 amp fuse that's going to be inside of here, or a 50 amp circuit breaker. If I have got a fault that is going to go and happen, let's say that this line shorts to ground. When that happens, I'm going to get fault current that's going to flow. That current is going to flow through the entire circuit. And it could be a large amount of fault current. Let's say that the fault current that develops is going to be 800 amps. We'll talk about development and fault currents once we go into some of our grounding and bonding. We'll see exactly how big these things get and how quickly. But if I've got 800 amps of fault current that's flowing instantly over here, it is big enough that it will trip each of these out. But what I'll want to have is I'll want to make sure that this one trips slower at 800 amps. Let's say that this thing might take 15 seconds to trip at 800 amps. And then that this one over here might go and take, we'll go and say this thing's 8 seconds to trip at 800 amps. And this one over here might take 0.5 seconds to trip at 800 amps. What we have over there is called coordination. And the coordination means that all three of these could be tripped by that 800 amp, but the one that's closest to the actual fault, the smallest, the least important one, will be the one that, has to sacrifice, kick itself out in order to go and interrupt that. The way that this would be done on graphs is that you would see for each of these graph lines that are going to go and look like this. If I were to go and be taking a look at them, actually I can draw these properly. Why don't I draw one properly? We'll draw for the 600 amp. It's going to be starting right over there. See, that's my 600 amp curve. And then we will draw this blue one over here. That's going to be my 200 amp curve. like that. Now when you go and take a look at any value that you might have over here, you know, that 800 amp, we could actually track that up over here. I know I just gave it numbers there before because we didn't bother drawing it out, but I could see that that 800 amp would go and trip over here. It's not bad. It was a pretty good guess there, somewhere around the 7 to 8 seconds. And that this one over here, well, that one's taking a little longer than what I said. It's going to be roughly about 150-ish seconds before that one would trip out for those curves. That would be proper fuse coordination. What you should always see is that the lines do not cross. No crossing. As soon as I allow the lines to cross, then I'm going to go and run into this issue where I will have non-selective coordination. Let's go and take a look at a non-selectively coordinated one here, where we will have, actually I'll keep that one inside of there. The blue, we will start the thing out at 200 over here. And then we will take this one, and we will start that one over here on my 800, or certainly 600. But now I'm going to go and cross over here. This would be a bad situation because, hey, come back here. Because what I would see then, if that red is my 600, and if the blue is my 200, I would see that if I go and have a large fault right over here, so up until this point, I would be fine. Anything below that, I'm going to go and have the blue that would interrupt first. But past that, if I get to like a 3,000 amp fault, I'm going to see that I'm going to be kicking out my main, this one up here, before I would be kicking out, you know, that 200 or anything like that. As soon as the lines cross, there's always going to be problems. So just make sure that when you have these, that the lines themselves don't cross. Manufacturers have this available on the website. You just plug in, hey, I've got this and this and this and this, and it'll be like, it'll put it all onto the graph and let you see whether those things are going to be crossing. Excuse me. Circuit breakers are going to go and have the exact same thing. They're going to be drawn, though generally speaking, as being wide bars because the circuit breakers themselves have a bigger operating range based upon ambient temperatures and a bunch of other factors that we'll cover when we look into them. But they will have similar looking ones over here where you would once again be able to go and track out your amount of current and how quickly something is going to go and react. Over here, we've got a 90 amp circuit breaker and we've got a 400 amp circuit breaker. I see that the 400 amp circuit breaker doesn't start its line till above 400. And I see that the 90 amp doesn't start its line till above 90. I know that these are way cut off. They are a bit snipped over here, but we would be able to see any sort of a fault current. If I were to take a look at a fault current of 800 amps, I would see that this one here should be tripping anywhere from 0.1 at a minimum all the way over to 6 seconds at a maximum. Anywhere inside of there, it could be tripping. Whereas this one over here, that 400 amp at 800 amps, is not going to start tripping till 60 seconds in off of that. Same deal, it's just a wider set of lines that we navigate through, so we see a bigger range across them. Yeah. We do have to just deal with, loads that sometimes do give us inrushes or, stuff gets stalled and we have to kind of chug through it, so we will see some of these small little issues that pop up, but overall, it's not a massive thing that you're going to deal with on a day-to-day basis. It's usually going to be taken care of by engineers. If not engineers, the easiest way for you to take care of fuse coordination is by the same manufacturer. If you have a Siemens, entry for your building, that's what your service is, and you've got Siemens breakers inside there, and then you switch over to some Schneider products, and then after that you're going to switch over to some Cutler Hammer, you're going to have an incredible hard time coordinating that. Whereas if you use a single line of components, let's say you pick a square D line of components and you go all the way from your main service all the way back in, they're going to be inherently coordinated by the manufacturer. This is why we like to stick with them, why we should be keeping the same types of panels and switches and things like that inside of a installation. Time delay fuses are going to have special markings out of our code. We are going to be required to mark anything that's time delay is going to have a D on it. Anything that is going to be non-time delay is going to have a P for a low melting point on them. Inverse time current characteristics is what has been described inside of this section. We just went through the coordination of that, so let's go and move on. Other considerations that they have inside of here for you to worry about are going to be ambient temperature. Heat is going to be a big deal. If I have got a fuse or a circuit breaker, those are going to be responsive to heat. And so if I put them into an area that's got a high ambient, I'm going to go and trigger them early, and can lead to possible faults where it's not actually an issue, but it's just that stuff is too hot. Boiler rooms are notorious for this. Circuit breakers that have been placed inside of boiler rooms are tripping out all the time, and you can't replace them with a bigger circuit breaker. You're not allowed to go and do that. But the reason is the heat that's inside of there. You might even have to go and apply cooling to that panel. Sometimes you will go into some of these places where you will see fans that are being used to cool certain aspects. If I've also got heat generated by loose or corroded connections, that can cause problems. And if I've got excessive vibration, the vibration can weaken fuse links, or it can go and cause some of my circuit breaker components to also start to jiggle loose, really, and then cause early trippings. Okay, let's go through our fuse types. First type of fuse over here that we're going to take a look at is going to be a plug fuse. Now, all fuses inside of them are going to go and have what we refer to as the fuse link. And before we go through and take a look at all these, I want to go and take a look at a fuse link itself and how that operates. What we get inside of a fuse is there's going to be places of restriction. R is equal to K times L over top of CMA, right? We know that wherever I'm smallest, I'm going to have the highest amount of resistance. Now, the fuse is a series circuit, which means that my current is going to be the same through all components of this. But what I'm going to get is I'm going to get different watts at areas like this. Why? Because I squared R. And areas like that, the actual link over there, have got a higher resistance. Therefore, they're going to have a higher wattage. So we're concentrating heat inside of these things so that we can trip stuff out. What happens, two different cases, depending whether we're dealing with a short circuit or an overload. An overload is going to be a mild amount of current increase, anywhere from 1 to 6 times. If I take a look at this, we're going to look at this under a overload, so I'm pulling more current through than what I should be. Maybe it is a 20 amp fuse and I'm pulling 30 amps through. As a result of that, these fuse links are going to go and heat up. Now, this chunk over here is going to be radiating heat, and that heat gets picked up by this, which is also radiating heat, which makes this section even hotter, which radiates its heat over here, and so then I end up with my central link that is going to be the hottest. All of these are going to be pushing heat towards the central link inside of here. And that central link is going to get too hot. It's going to be made out of like a zinc type of alloy inside of there that will go and melt early on. And as soon as that thing melts, it opens, right? It just falls away. So it starts to go and melt. As soon as it melts, it is going to establish a tiny little arc. How hot does an arc burn? About 3,000 to 30,000 degrees. So massive, massive temperatures. That arc is going to quickly heat up the rest of this, and it's going to burn across here. So the arc is going to burn across here, and it's going to be melting that away as it goes. And then eventually the arc gets too big to support itself. And as soon as it's too big to support itself, can no longer ionize the air and maintain that current flow, it's just going to drop out. That's it. We're done with that, and then we no longer have current flow that's going to be through there. Sometimes we will have other stuff that will flow in, our quenching medium, that's going to go into these things. It could be silica sand, or it could be boric acid. Both of those are commonly going to be used. Don't open these things up. It's pretty clean white sand, but don't take it home to make like a beach diorama or something like that, because in a lot of cases it also contains boric acid. Not terrible, terrible stuff, but not something you want to be playing around with either. Silica sand is the base for glass. We heat this up to 3,000 degrees. That is far, far lower than the melting temperature of glass. So in other words, the silica sand will melt, turn into glass. Glass is a very good insulator. So we're going to go and get glass that will just flow into here, and it's going to seal those ends off. Boric acid is going to be a snuffing compound, which means that it is going to go and remove oxygen, or the ability to burn, the ability for this arc to actually be burning across there. It creates gases that help to go and interrupt the arc, is all that we have that mixture inside of there for. That's how it will react underneath a overload. Underneath a overcurrent, that would be a short circuit, we are going to get all the fuses that are going to go and melt almost instantaneously. And this is really handy for us if we're dealing with a fuse that has blown. We don't know why the fuse has blown. We get a customer, and we're a little bit leery about turning that thing back in because we don't want to close in off of a short circuit. So what we can do is we can open up that fuse if you want. You're just going to take a hacksaw because they're usually going to be a fiberglass can or something like that. You're going to wear your dust mask and you're going to wear a set of gloves so you don't get glass fibers in your lungs or anything like that. But a hacksaw, you can quickly ring around the outside of that fuse. You can open that thing up. If all my fuse links are separated, I've had a short circuit. That's a massive fault on the system over there. I probably want to make sure I clear that if I don't know what already caused it. If they're like, yeah, the tree fell over there on the lines, you know what caused it. You clear that, you're pretty safe to go again. But if you don't know what caused it, you want to go and take a fairly thorough look through that system before you turn it on. If you've only got one of these that's gonna blown, it is probably just an overload. It just means that they've had too much current that has been flowing. So, you're going to shut off a couple of panels, and then you're slowly going to bring the load back on while monitoring with an ammeter to make sure that it's not getting too high. That's what's inside of every single fuse, is going to be these, what we refer to as fuse links that are going to go and melt out. Now let's talk about the individual fuse types there. Really, we got a couple of old ones here that are not going to be seen a load anymore. That's going to be my plug fuses. Also referred to as screw base or Edison base or E26. E26 being the size of the fuse holder. Edison base, 26 millimeter. They are going to be W's, which is going to be a standard, or they could be a D, which is going to be a time delay, and these are going to be limited to no more than 30 amps. You will see really old fuse panels that will utilize these. It is the exact same base as what we use for a standard light bulb, what we screw stuff into. You're not supposed to be using these on anything that is more than 120 volts off ground. And you're not allowed to have these things be interchangeable, right? Whereas the customer can thread out a 15 and be like, well, I keep tripping that circuit. We will put in a 30 over here. They're not resettable. Well, actually, I should say they're usually not resettable. There are some breakers that have been specially made to plug into these. But the fuses themselves would be non-resettable. The one place where we do still see these things utilized is sometimes when you are dealing with overhead lighting, where you've got a triplex that's running to this pole, and then from this pole running out to another pole somewhere over there. What you'll sometimes have is you'll get one of those lights, just an arm light that's going to be placed off the side over here. That arm light needs to go and have power supply to. Now, you might have a 200 amp triplex that's going across from pole to pole to pole because you're feeding from one building over to another building, but you decide you want to drop a light inside of there. What you will see is pigtail lamp holders. Everybody should have seen a pigtail lamp holder once or twice in their apprenticeship by now. It's going to be a black rubber lamp holder that will have two flexible leads that's going to go and come off of it. There's going to be a white lead, there's going to be a black lead. Those two flexible leads, usually we place these inside of places like a crawl space or something like that where we got a low ceiling height. We can't have rigidly mounted bulbs. You'll see these things being screwed into there where somebody will tap off of one of the live lines over here. So off of line 1, they're going to go through one of those pigtail fuse holders. Our pigtail, it's a light holder, but then they will screw one of these into that, and then they will use that to feed the light, and then the light goes back onto the neutral so that it's protected, it's not running off at 200 amp. All right, talking about identification, we do have type C fuses. These are going to be older ones that are going to have a rejection ring. The rejection ring goes in the bottom of the socket. So at the very bottom of the socket itself, this thing is going to be placed down there. We know that the hot contact is going to be in the very center of that socket. So whatever I place into here is going to get, spit out by rejection rings. There's a color coding to them. Blue is going to be 15, pink is going to be 20, green is going to be 30. Breaker manufacturers used to even follow these. If you take a look at old Federal Pioneer or Cutler Hammer breakers, you will see blue 15 amp breaker handles, red 20 amp breaker handles, and green 30 amp breaker handles that you will see off of those. These rings are going to be placed inside of there. They're going to have different diameters based upon what we have for availabilities. This over here is a 30 amp ring. It's going to have a fairly large hole. A 50 amp is going to go and have a fairly small hole. And if I've got a 30 amp plug fuse, that 30 amp plug fuse is going to go and have a large male contact on the bottom. That large male contact would allow it to be inserted into here because that large male contact can actually fit inside of there. This one over here, the 50 amp, that's only got a very small hole over here, that's, as soon as we bring that thing down, it's too large. It's not going to be able to go into there, and so it's going to reject that. So your customer cannot go and increase it without them fishing around the bottom and removing the rejection ring. The rejection rings do come out on these ones. they figured out that that was a problem. You know, they initially put the rejection rings in so people couldn't screw around with them. Then customers screwed around with them anyway, so then they moved to this Type S. Type S has got an actual rejection ring that is not removable. It's a harder fuse to go and find. It was kind of only in there for a bit, and then they were saying, look, we're getting way too complicated, let's just go to circuit breakers. We don't see a lot of them, but they do show up from time to time. Most cases where you're looking at a plug fuse panel, though, you're usually going to be pulling those things out and replacing them. The more common type of fuse that we will see is going to be a cartridge fuse. And cartridge fuses are going to be either standard or HRC, standard being our 10 kiloamp, HRC being up to 200,000 amps. And then they're going to come in two types, ferro contact and knife blade. Ferro contact are going to go and have jaws that these are going to go and push into. Knife contact are going to go and have jaws that these are going to push into. These are not pins on the end. They're actual, excuse me, actual blades on the end of the fuse. Elongated blades that look like that. And so we shove them into, you know, the jaws of our fuse holders that we are going to have. Very similar to the end caps, you know, and everything. We're going to have our fuse element that's going to be on the inside. The barrel of these fuses is always going to be made up of an insulating material. There will never be a live component on the barrel. The ends of these absolutely could be live. Be very careful when you are removing fuses. You should have a proper fuse pulling device. It's a fiberglass, you know, grippy jaw thing that allows you to yank stuff out. But the barrels themselves will always be safe to touch, not the ends, though. Be very careful around the ends. Fuse construction on the inside, we did talk about what that is, you know, that it's designed to be the weakest link and it's designed to go and melt. And we create the melting point, an engineered melting point, by reducing the circular mill area and thereby concentrating the actual heat itself that we are going to have inside of here. Some of them are going to be renewable. We have got non-renewable fuses, or what we refer to as one-times, and then we are going to go and have renewable ones. All that a renewable fuse has is the ability for us to go and pull them open. On some places, particularly where you have loads that, you know, intermittently get jammed up, motor type of loads and things like that, where they can blow, in some larger installations, they will request to go and have renewable fuses. You generally don't see these unless it is done at a place that is going to have a maintenance plan, maintenance personnel. What happens inside of these ones is that we just replace the fuse link. We can take the fuse out, we buy a whole pile of these fuse links, which are cheaper than the whole fuse itself, and then whenever one blows, you know, the maintenance electricians figure out why it blew, clear the problem, and then they're going to go and replace it with another fuse link. Ferrule types are going to get slid in there. They get twisted around halfway. You see there's a slot over here, so it's going to insert it in there flat the way it is right then, and then you can give it a half twist. You then cap it on either end, which clamps it down. Knife blade types are going to go and have an insulating bar. That's this one over here. That insulating bar is going to go and have a bolt that's going to go through to your knife blades, and you're going to go and bolt the actual fuse link itself onto that one there. Okay, we're going to skip past the next two drawings because we did take a look at them. The reactions underneath a overload and underneath a short circuit. And let's go and take a look at this one over here, which is going to be a dual element fuse, also referred to as a time delay fuse. A dual element is going to be able to respond to either a massive amount of current, a short circuit, or to an overload. Now I'm going to go and have two separate sections inside of here. This section, that's going to be my fuse links, is going to be engineered to respond to short circuits. That's all that fuse link section is designed in there. All the current flows into here, and then it goes to these discs over here. These discs are going to be conductive. We'll just place those two discs over there. That is all going to be conductive. Then what we are going to have is in between those two conductive links, we are going to go and have a spring. Now they are showing in the background over here another plate inside of there. Some of them do have that, some of them don't have that plate on the inside. If they do have that plate would be made out of insulating material. But in a lot of cases, what they'll have instead of that is they're just going to have a fuse link inside of it. And what it'll look like, and I'll just draw my own over here because it's a little bit hard to see off of theirs. They're going to go and have the one end cap. They're going to go and have the other end cap. This is where, you know, we have our lines coming in. And then they will go and have what we refer to as a pigtail or a shunt. And that pigtail is going to be a flexible copper lead. A flexible copper lead is going to go and get run all the way up to the top over here, where it's going to go and have another disc. And that disc is going to get placed up against this disc here with a blob of solder. And it's going to be a solder that's going to be a low melting point solder. What we are also going to have is we are going to go and have a spring that's going to be tensioned. We don't want to carry the current through the spring because that would cause the spring to go and anneal. But the spring is going to be tensioned all the way across, and it's going to be pulling down this disc. Now, normally this disc is soldered up over here, and it is going to be, bolted hard or brazed onto that end over there. So all of my current comes into the fuse, flows into this disc over here, and then it flows up the solid shunt through the solder and up top over here. If I get an overload, the solder is going to heat up, and it's going to be what we refer to as eutectic, meaning it goes suddenly from having a solid to a liquid. Eutectic solder will be fine, and then boom, it's going to go and trip out. It'll trip out at a lower amount. It'll basically allow us to have that time delay. Once it does trip out, the spring is going to yank this piece back over here, so it's no longer going to make any contact inside of them. These are going to go and have the letter D. The D does not stand for time delay. We do say, time delay fuses are marked with a D. The D actually just means dual elements inside there, but we refer to it as a time delay. Type P fuses that we are going to have are going to be not time delay. They're going to be a low melting point and an instantaneous, and they're going to go and have a low amount of interrupting rating. Type Ps are going to usually be limited to no more than 10 kiloamps. There are some specialty ones that will go up from the 10 kiloamps. They'll go up to 50,000, but they're still going to be fairly low. The bulk of the rest of our fuses are going to go and be HRC types of fuse. Oh, look here. I have a better picture for a dual element time delay fuse. Same thing, what we just talked about. I forgot that I'd inserted this one into the slide pack I was just working on for the book there for a second. Same thing, you see the overload element in the center, you see the short circuit element over there, and you see this thing is yanking that open over there. The next bit of the book goes through a whole pile of different fuse types. Class R's that we are going to have available as ferrule or knife blade. We're going to go see Class J's. We are going to go and see HRC1, HRCT, L fuses, a whole pile of different types. I'm not going to go over these in depth. Read through them, take a look. That's on you to go and read. But what I do want you to note about them is that they are physically different in shaping and in sizing that they're going to go and have. A lot of them are also going to go and incorporate anti-rejection features, rejection features. These are going to go and prevent us from using other types of fuse. This one over here is going to have a little ring, which means that the jaws that go inside of here, or the jaws that it goes into, are going to go and have a little blade that's going to go and stick out like that, and that's going to prevent other fuses from being placed into there. Same with these ones over here. This is going to be a rejection feature, the size of that hole. What I'll be able to do is I will be able to run a specially sized bolt through my actual jaw blade, and based on the size of the bolt, I can use that to reject certain sizes of fuses. Just prevents us from having spiking, where somebody goes and puts too large of a fuse inside of there. All of these are going to go and have different sizes, and they're going to have different ways that they're going to incorporate rejection feature. You get rimmed cases over here. You're going to go and have short lengths, all sorts of different things that will provide those rejection features. I'm going to move past all of them. Do take a look through. These ones are pretty common, by the way, the HRC1, the CC class fuses for small components. The other ones that are really common were my L's for my large ones over there. We're going to move past all of that, though, and we're going to take a look at the circuit breakers. I'll flip a bunch of pages here myself. Other fuses, actually, before we go into the circuit breakers, they do give you a short little blurb on other types of fuses. Semiconductor fuses, midget electronic specialty fuses, for locomotive lift trucks, etc. Once again, these are all specialty ones. The semiconductor fuses are going to be a special one used when we have got drives. You do need to use special fuses. You shouldn't be using regular ones. You should be using stuff that is compatible. The way that you figure that out is not by looking at the fuse manufacturers, but be looking at the VFD, the motor drive manufacturer, and see what they recommend for a fuse. If they've got specific fuse recommendations, it's because they are trying to prevent damage to the semiconductor component. Fuses are designed to be sacrificial. They're designed to be the weakest link. Drives are going to cost thousands and thousands of dollars. Fuses can be anywhere from $100 to maybe a couple $100. And so what happens inside of situations is people say, well, that fuse is $600 fuse, and this fuse over here is also rated at 100 amps, but it's only $50. I will buy the $50 one. That $600 fuse was designed to go and protect, or it was specified to protect a $5,000 drive. The $50 one's not going to be able to do that because it doesn't interrupt as quickly. Make sure when you're dealing with drives, you're following the proper manufacturer's fusing recommendations. Those semiconductor fuses, they will give you lists of which ones to go and use. Okay, looking at our circuit breakers. Canadian Electrical Code has a definition for a circuit breaker. You can go into section 0, you can read that yourself, but it is going to be a resettable device that can respond to overloads, over circuits, and is not going to injure the device. In other words, there's no solid amount of damage that is going to go and happen to it. They are also specified as having to be trip-free. And trip-free just means that these things are not going to be able to be held. You can get a customer that says, hey, I see that little hole through the handle over there. I will just take a little chunk of wire or string and I will tie this thing so they can't go and trip out. Even if the handle is held, the internal guts of it are still going to be able to go and operate and trip that thing out. Circuit breakers, you should be familiar with them, come in two main types. We're going to have bolt-on types where we have to bolt onto the live lug. You'll see that with usually a little tab that's going to be pushed out to the front with a hole through it, and usually a captive screw. That's going to be a screw that doesn't just fall out of there. You place these things to the panel and then you bolt them down, obviously while the panel is turned off, not just with an insulated screwdriver. Push-ons are going to have a little set of jaws in the back. That's what this one actually is, and you just shove that thing onto what it needs to be. Breakers should also have some way to indicate when they're tripped. Some of them are going to go and have a flag that shows up in a window. It'll give you that little red or a yellow flag inside of there, like the square D one that they have over here. Other ones are going to be that they're going to just off the breaker handle position. It'll move to a central position. For every circuit breaker out there that I have ever run into, and maybe there's an oddball that breaks the mold, but every single one, if you're resetting them, what you need to do is you don't just turn them back on again. You have to push them all the way to the off to reset them and then kick them to the on. You're ever not sure if a breaker is tripped or not? Push it to the off. You'll hear that little click, feel a little bit of friction as you move stuff back into position, and then when you flip it on, that thing comes back on. Do note on top of here that this thing has got its rating. It's got a 120 240 volt rating. That's going to be a slash rating, so we cannot use this on a 208 120. And it's got the 10 kilo A. 10 kA, that's going to be its interrupting rating that this thing would be good for. It's also got a manufacturer's designation. It's a trademark over there, square D, so you can go and look it up and you'll see a bunch more information that's going to be imprinted or molded into the side itself. One thing I want to point out, by the way, on the way that these are laid out, there's a big difference between 208 120 and 120 240. See how the bigger number precedes the smaller number, and then on this one, the smaller number precedes the bigger number? We've talked about this before, I know we have, but that designates whether something is going to be three-phase or whether it's going to be single-phase. If it goes from big to small, it has to be a three-phase rated one, so it would be utilizable in three-phase. If it goes from small to big, then it's going to be a single-phase rated one. This one, by the way that they lay that out, tells me it has to be used inside of single-phase panels. You cannot be using this thing in a three-phase panel because it's not rated for three-phase. The layout of the words itself tell you that, or should tell you that, or should tell your journey person that, whoever they are. They might not be aware of this as well. It's something that kind of flies under the radar and a lot of people just don't know about. Okay, breakers themselves are going to be made up of different elements or components inside of there. We are going to go and have thermal components. We're going to have thermomagnetic components that are going to respond to both heat and magnetism. We're going to have some that are magnetic only and some that are going to be solid state. In other words, they're going to be basically a meter that is going to go and read and trip. The big thing that we like about them is the fact that we can do that, the off to on, and we can reset them so that we don't have to buy a new circuit breaker every time that one goes and trips out. Inside of there, because they are going to be reusable, we have to have some way that they can open and operate without causing a lot of problems. And what we will see inside of them is a way to go and safely dissipate the arc that happens. If we have got a fault, we can assume that that thing is going to be many times the breaker rating in amps. And that means it's going to be a hot arc, and it would be a damaging arc. And we would not want it to go between the actual switching contacts of the breaker itself, because it's going to pit and corrode those. So what we will have is we will go and have a set of what we refer to as our arcing contacts that are going to be spring-loaded. They're going to be sacrificial contacts. And then we are going to go and have our main contacts. These ones are always going to be spring-loaded, so that they want to push forward. That's just what they want to do, which means they're always going to be sitting a little bit forward. So when I'm closing the circuit breaker, we'll ignore what it says inside of here right now. Anytime that I'm closing the circuit breaker, as I'm pushing these things in, this one will make contact first, which will establish current flow through the circuit breaker itself from one side to the other. And as this thing closes in, it then gets to that state over there. At that point, because my main contacts are going to be larger, stronger, and they're going to have a smaller CMA, larger CMA, the bulk of my current is going to want to travel through them. So I'm going to have my main current that's going to travel through there. When I get to the point that the breaker is either being, flipped open by us, or where it's starting to go into a trip type of situation, what happens is this whole set of bars starts to go and open up. And what we see is that this then happens where the main contacts separate. My current is not going to jump across that gap. It's going to take the path of least resistance. Air is highly resistive. It doesn't want to do that. That sounds like a big pain. So instead, it is going to travel through the arcing contacts, and then it is going to go and establish an arc across those arcing contacts. At this point, this is too wide. It's not going to be able to arc across there. It is only going to be able to go and arc across there, and then what we can sometimes do is we can then drive that up into an arc chute. That's what this diagram is over here. They're just taking a look at the arcing contact, which is opening. It's pulling across this arc chute, and as it pulls across the arc chute, the arc itself gets established in here. These are going to be flared. It's hard to see it off here, but each of these is going to go and be flared. The reason that they are flared is because heat is going to cause expansion, and that expansion is going to go and force this thing further out. So that arc in the bottom over here is going to expand the air, and it's going to push this thing up the inside. And as it pushes that thing up the inside, because it is wider, it is a bigger gap, and therefore it's harder for it to maintain that arc. It just allows us to go and snuff the arc relatively quickly inside of there. You'll see these on the sides of circuit breakers, sometimes on the ends of the circuit breaker. This one here doesn't show it because it's sitting down here, but usually it'll be on this end underneath the conductor. Sometimes you'll see a little brief, blue flash as you open and close a circuit breaker, and what it is it's just directing that arc out of the side of it. Molded case circuit breakers are going to be our most common type, where we are going to go and have a case that is going to be made out of plastic, and then we are going to have all the components inside. Not everyone is going to be the exact same, but they are going to have some common things. We cannot just interchange, different manufacturers from one to the other. There's going to be frame, which is going to go and give us usually the mounting. It allows us to snap into the panel. There's going to be an operating mechanism. There's going to have to be some sort of a handle, obviously, for you to operate it. Inside of there, there's going to be the actual trip elements. Poor low-quality drawing over here, but something that is going to sense the current itself. And then there's going to be the contacts, which are actually going to be the two components that are going to open and close. In this case, they got that bar that would go down to here, and then would go and pull up across my arc chute over here. Operation, or our operating mechanism, is always going to be spring-loaded. Even if we push it slow, what's happening is it is building pressure, and then there's going to be a sear that will go and release that pressure, and boom, that thing is going to go and kick in. Or if we're opening it, same deal. We feel pressure, and then boom, it snaps out. All that does is it makes sure that there's a really quick activation. Because the faster the activation, the less watts that are going to go through, the less time that I'm going to have for an arc to be established across it. Trip elements inside of there are going to be made up of two main types. We are going to go and have magnetic elements, and we are going to go and have thermal elements. And they're both going to respond to different things. Magnetic elements themselves are going to be overcurrent, and then thermal are going to go and be overload. And thermal elements will be made with a bimetallic strip. We've talked about these before this year. Two dissimilar types of metal that are going to be bonded together with, super tight epoxy. And then they're going to expand at different rates under heat. And because they're expanding at different rates, the one that expands more, the red over here, is going to go and push the other one over. So we can anchor this end over here, and because it's going to start curving in that direction, we can place something over here that it will contact. That's what we're seeing inside of here. My main path of currents is a poor low quality one is going to be through this conductor over here to that set of contacts and out like that. As that current flows through here, it is going to go and provide heat, I squared R, right? And so it's going to start to heat this thing up. If I've got too much current, I'm going to have too much I squared R, too many watts. And this thing will start to bend over, and as it bends over, it will go and eventually make contact with a trip element over here. That trip element is then going to go and cam. There's a pivot point right there in the very middle of that thing. So it's going to cam. As it cams over, then this, which has also got a pivot point, it's got a spring that's pulling that thing down, but right now it's locked over top of that one. Once we push it out of the way like that, and this thing pivots, that spring can then go and pull this down, which is then going to lift that other end up there, just levers, which is going to interrupt my current. My current can only get up to here, and it cannot go across to the other side. So it takes a while for my thermal element itself to go and operate. It's designed to protect against any sort of overloads. If you've got a high ambient temperature, though, you place your panel someplace where it's really hot, where you've got a hot breaker sitting next to it, you can get nuisance tripping off. Magnetic elements are designed to go and be instantaneous based upon the overcurrent. If I get a large overcurrent, a short circuit, I'm going to go and build a large magnetic field, right? We know that phi, amount of magnetic flux, is equal to my ampere turns. And so what I will have is I'm going to go and have my current, so I'll just draw that with the highlighter here, is going to go through a bunch of turns. Not a lot of turns, usually about 5 or 6 turns inside of there, and then it goes down, and we see that same path that's going to be going through there. In the case of a short circuit, I'm going to go and get a large magnetic field. There will always be a small magnetic field over here, but in the short circuit, I'm going to have a lot of current, therefore I'm going to have a lot of flux. And what that flux does is this coil that's running through there, it is going to try to find the path of least reluctance, so it is going to go and grab pieces of metal, and it's going to pull them in. This plunger over here, this is going to be an iron core over there. And so it's going to pull that plunger in. When it pulls that plunger in, once again, we're going to go and toggle this trip bar over here. The sear will go and release down below here, and that spring can pull that thing down. It's going to go and interrupt our current. Our current can only get through up to there now. We cannot pass all the way through. These are very simplified versions that they have inside of here, but you should be familiar with what each one does. Magnetic responds to short circuit. Just write that next to it. Short circuit. This one over here, overload for my thermal component. We do have some breakers that are going to be magnetic only. They're going to be referred to as an instantaneous trip. They're not going to be doing anything, and then we hit that threshold and boom, they're going to go and trip these things out. We do usually have the ability to adjust how quickly they're going to go and operate as well by adjusting. There's going to be a little trip element that is going to be, on this side over here. You can sort of see it inside of there. They show a diagram on the face, and then they show right beneath it, you can see it molded in right over there. That's going to be a trip element that is designed to be adjustable. These are good for the fact that we can get one large frame. Your frame might be good for 800 amps, but then the element that's inside there, you can adjust from 800 all the way down to maybe 400 inside of there. So we can set these. These, by the way, these trip elements themselves, and the adjustment for them are going to be covered by the faceplate. When I stick a faceplate over top of this circuit breaker, it's going to have a cutout right over here for the handle, but everything else stays hidden. This is a really good thing because that prevents anybody that's on the maintenance end from being like, well, I hate this breaker because it trips out all the time. I will just crank it up. We always want to keep that stuff hidden from our day-to-day maintenance personnel because they're not trained in it. You are trained in it, and so they should not be screwing around with it. You're allowed to screw around with it, intelligently, of course. They're not. High interrupting capacity ratings are going to go and be used for large amounts of short circuit. Most of my standard circuit breakers are going to be limited to 10 kiloamps just due to the way that they operate. They cannot rupture nearly as high as what I'm going to have for circuit breakers, for fuses. If I need a high rating on my circuit breaker, I need to get one of those high interrupting capacitors. But even them, they're not going to be that high. Topping out around, at this point, manufacturers are topping out about 100,000 amps or 100 kiloamps, but it's not that easy and they're very, very expensive. Magnetic-only breakers that we were just talking about, they only respond to short circuits, which means that you would have to have other overloads. You'll use them, generally speaking, inside of motors or something like that, where you're going to have an overload attached to the motor itself, and then your breaker's there just to protect the lines from short circuits. High interrupting capacities, they are going to be able to go and interrupt both of them, but they get very, very expensive. Solid state breakers are basically an ammeter that is going to be in line, that's going to be monitoring. So you take a look at the actual casing of that thing. You're going to have a line that's going to go into there. There's going to be a little CT. That little CT is going to go into a little electronic board. That electronic board is going to be monitoring the current that is going through there all the time. And then it is going to go and activate a set of contacts to go and open that up. They're getting more prevalent. You know, they monitor it, and then as soon as it operates, you know, they're going to be or as soon as they sense too much current, they're going to be able to go and operate. What we're getting is we're getting smarter and smarter systems. And so solid state breakers are starting to become bust. Rather than having to have, you know, pull the cold cover off to go and access the trip element that we have over here on this instantaneous one, what I can do is I can program that now remotely. If I have got a smart system, they're expensive, but useful inside of industrial applications, I'm going to be able to go and have breakers that are networked, where I can go and adjust. I'll say we'll call this thing breaker number 1. And I'm going to have a computer on the system that is going to be monitoring breaker number 1. Breaker number 1 will operate without the computer. It has to be network free, but I can monitor it through breaker number 1. I can see how much current I'm pulling through there, and I can set adjustments. I can say that, hey, when this thing reaches this amount, I want to allow an overload of, 120% for up to 5 minutes. And past 5 minutes, I want that thing to go and trip out. So you can program that in. This thing then stores that inside of its internal memory and, sits and waits. You can also program in that, this thing is going to have a maximum continuous rating of this and then a short circuit rating. I want it to respond like so. And so what you're able to do is within a set of parameters, obviously within a frame size, you can basically build your own custom response curve. And that response curve gets communicated to this, stored in there, so that if for whatever reason that Ethernet cable gets cut, it is still going to be able to operate. Expect to see more of these in the future. Not in your houses, but inside of large industrial types of applications. GFCIs that we have, or ground fault circuit interrupters. Okay, a couple of older pictures from some of the older modules here. That's a magnetic-only breaker. They're showing, the adjustment for the trip knob off that one. Here's an HIC breaker, high interrupting capacity. Oftentimes, these HIC breakers are actually breakers that contain fuses inside of them, and you have to replace a component of it. It's still a fuse, but, they call it a breaker component at that point. Taking a look over here at a GFCI, we have talked about GFCIs under our instrument transformers and the fact that we are going to use a CT that is going to go and monitor what is going on inside of our circuit. So we're going to go and pass current through. All of our current should go and pass through there, and if our circuit is good to go, all of our current should go and pass back out over here, right? Which would mean that the amount of flux is going to go and be 0. Phi is equal to ampere turns, but my net amount of amps, because I got some amps in this direction and then some amps in that direction, cancels out to become a value of 0. So I get no net flux inside of it. As soon as I go and have a leakage to ground, even if it's just a tiny little bit of current, that's going to be able to go and transfer back to my neutral. So it's going to leak to ground, where it's going to travel over top my bonding path and back to the neutral. That means that now some of it's going to split off and travel around the outside, so I'm going to have unequal amounts. Basically what we looked at there before, those two vectors, now one of those vectors is going to be longer than the other. So it's an unequal amount, therefore there is going to be phi equal to ampere times turn, right? Because we get a net amount of amps inside of here. It's going to go and trip out, and then, that whole thing, it's going to sense that, it reads that it's the type of solid-state breaker, and then it's going to go and activate. This over here looks like an inductor. What it's standing in for is the coil. It's just going to be a magnetic coil that's going to go, and it's just going to go and magnetically pull this up so that it's going to go and operate. A better picture of it looks like this for how we actually connect these in the fields. What we will have is oftentimes we will have pigtailed ones, although we sometimes do have ones that snap onto bus bars as well, into our neutral bus bars. Some of like the Schneider Homeline, or I think that Siemens has a set as well where you can snap them on. But what we will have to do out in the field is we bring our neutral and our live lines back into the circuit breaker. Over here, we see it's cut away at the circuit breaker. This is where we would plug that thing onto the circuit breaker, and then we would have to go and connect this onto our neutral. It's going to be that pigtail that we are going to go and have. Following my main path of current then, I can see that I'm going to go and have a live line that would be able to go and travel through this out to my receptacle. From my receptacle, I would then be able to go, and we will just draw this as a resistor over here, plug that thing into here. So I'm going to have it going in and then coming back out. So follow that through our receptacle. Come out the hot line of the receptacle, travels back through my load, back into the receptacle, back into here, and then I follow that one up through and back out to neutral. So we see we got a complete path over here. If I took my line, my neutral that I had coming back, and instead of running it into here, if I didn't do that, but instead I directly took my neutral over to the neutral bus bar over here, what we would see is that my current at that point would bypass. I don't have it all going through here. And as a result, when I try to turn this circuit breaker on, it instantly trips, right? It's got absolutely nothing that it's going to be reading for current. Or it might initially turn on if there's no current flow inside of the circuit, but the first time I plug a load in, it's going to go and trip out. That's why we're connecting these lines always directly into that circuit breaker. Re-highlight that line one more time, and it goes in and it goes through like that. So that's going to be my complete path for current. We've got that little CT over there. We see that the CT itself is going to be reading all of my line current that's going through it. The CT is going to have a set of leads that are going to go to an electronic control board inside of there. That electronic control board is going to go and have a connection over here to my line so it can get energized, as well as it's going to have a connection to my neutral. That's the other reason we need the neutral inside there, is just to run the microelectronics that are inside of there. And then it is going to read everything through the CT, and it's going to have an amplifier right over here. It is going to go and have a trip coil, which is going to be a magnetic coil. And when it senses that this thing should trip, either because of Gfci fault, some current that's flowing around the outside of the path to get back to the neutral, or as a result of having an overload or an overcurrent, it's pulling more than 50 amps through here, whatever, it will activate that. That is then going to go and magnetize. When it magnetizes, it creates a field that is going to go and attract that bar over there. So that bar is going to get pulled down. Right now we've got a spring that's pulling that thing up, but it's then going to get pulled down. When it pulls down, it is going to go and pivot. As it pivots, it is going to lift over here. And then that sear that we have over there that was holding this closed is then going to be released in this spring, which is providing outward pressure, pushes this bar out. That bar over there is then going to kick open. Basics of a ground fault. Ground fault types are going to be critical inside of our Canadian Electrical Code. We will see that inside of a lot of questions this week where we're going to be talking about outlet type protection versus circuit breaker. This is my circuit breaker type. We also can get AFCI outlets. We've got what are referred to as parallel arc faults that we could go and have inside of there. These are arc faults that are being designated on here, not ground faults themselves. Let's actually just talk about the ground fault first. The ground fault would be any time that this neutral would get a ground. Anytime that I would get a ground off of this, by the way, I'm going to go and have what we would refer to as a short circuit. Yes, it is going to be outside of the path, but that's going to be a short circuit current that will be tripping it. The guts for a ground fault, for an arc fault, are very similar. We just have got a different microprocessor inside of here that's going to be monitoring for stuff. Yeah, we can get AFCI, Gfci breakers that are going to have both inside of them. Those AFCI, Gfci breakers will be able to monitor all of them. Different types of arc faults we can have, by the way. Parallel arc faults, which are going to be in parallel with my load, right? My load would plug into here, so that arc fault is going to be in parallel with that. I can have series arc faults, which are going to be in series with the load. Whatever I'm delivering out to my load, back into there, that's going to be in series with it. And then I'm going to go and have arc faults to ground, which are another form of parallel arc faults, because ultimately the ground is going to be connected back to the neutral. All right. Oh, man, that is a long learning task over there, but we are through H1.